Hi, and welcome to the section Recurrent Neural Network. In this section, we will learn about simple RNN cells and RNN topologies, variants of the simple RNN cell, and stateful RNNs. Now, we move on to the video Simple RNN Cells and RNN Topologies. In this video, we will train a character-based language model on the text of Alice in Wonderland. Traditional multi-layer perception neural networks assume that all inputs are independent of each other. This assumption breaks down in the case of sequence data. RNN cells incorporate this dependence by having a hidden state, or memory, that holds the essence of what has been so far. The value of the hidden state at any point in time is a function of the value of the hidden state at the previous time step, and the value of the input at the current time step. Another way to look at an RNN, to unroll it. Unrolling means that we draw the network out for the complete sequence. For more information about simple RNN, refer to this website. RNN is simply a base class for recurrent layers. Next, we will learn how to generate text using simple RNN with Keras. RNNs have been used extensively by the natural language processing community for various applications. One such application is building language models. A language model allows us to predict the probability of a word in a text given the previous words. Language models are important for various higher-level tasks, such as machine translation, spelling correction, and so on. For our first example of using Keras for building RNNs, we will train a character-based language model on the text of Alice in Wonderland to predict the next character given 10 previous characters. We have chosen to build a character-based model here because it has a smaller vocabulary and trains quicker. The idea is the same as using a word-based language model, except we use characters instead of words. We will then use the trained model to generate some text in the same style. Open the Atom editor and click on the New File from the File menu. First, we import the necessary modules. We read our input text from the text of Alice in Wonderland on the Project Gutenberg website. Since we already downloaded this file and saved it as alice.txt, we will specify the input path to this text file. For that, add the text file path as input file. We need to extract as the stream of characters. Type in the print statement as extracting text from input. Then add a few lines of code from the code bundle. Note that the file contains line breaks and non-ASCII characters, so we do some preliminary cleanup and write out the contents into a variable called text, which is specified here. Since we're building a character-level RNN, our vocabulary is set of characters that occur in the text. There are 42 of them in our case. Now, add a few lines of code. Since we will be dealing with the indexes to these characters rather than the characters themselves, this highlighted code creates the necessary lookup tables. Again, add a few lines from the code bundle to create the input and label texts. We do this by stepping through the text by several characters given by the step variable. In our case, the value is 1, and then extracting a span of text whose size is determined by the seqlen variable. In our case, the value is 10. The next character after the span is our label character. Using this highlighted code, the input and label texts is specified. The next step is to vectorize these input and label texts. First, add a print statement for vectorizing input and label text. After that, add X and Y inputs from the code bundle. Each row of the input to the RNN corresponds to one of the input texts shown previously. There are sequence length characters in this input, and since our vocabulary size is given by NB characters, we represent each input character as a one-hot encoded vector of size. Thus, each input row is a tensor of size sequence length and NB characters. Our output label is a single character, so similar to the way we represent each character of our input, It is represented as a one-hot vector of size NB characters. We can define the RNN's output dimension to have a size of 128. This is a hyperparameter that needs to be determined by experimentation. In general, if we choose too small a size, then the model does not have sufficient capacity for generating good text, and you will see long runs of repeating characters or runs of repeating word groups. On the other hand, if the value chosen is too large, the model has too many parameters and needs a lot more data to train effectively. Finally, we're ready to build our model. First, specify the hidden size value as 128. After that, specify the batch size as 128. The number of iterations value as 25. The number of epochs per iteration is set to 1, and then the number of predictions per epoch value is set to 100. Once we've done this, add few model lines of code from the code bundle. Since we want to return a single character as output, not a sequence of characters, so return sequences is set to false. We've already seen that the input to RNN is of shape, that is, seqlen and NB characters. So it is specified in the input shape. In addition, we set unroll as true because it improves performance on the TensorFlow backend. The RNN is connected to a dense, which is a fully connected layer. The dense layer has NB character units, which emits scores for each of the characters in the vocabulary. The activation on the dense layer is a soft max, which normalizes the scores to probabilities. The characters with the highest probability is chosen as the prediction. Next, add a model.compile line of code. Since we compile the model with the categorical cross-entropy loss function, a good loss function for categorical outputs, and the RMS prop optimizer. Our training approach is a little different from what we have seen so far. Our approach has been to train a model for a fixed number of epochs, then evaluate it against a portion of held-out test data. Since we don't have any labeled data here, we train the model for an epoch and then test it. We continue training like this for 25 iterations, stopping once we see intelligible output. So, effectively, we're training for number iterations epochs and testing the model after each epoch. Our test consists of generating a character from the model given a random input, then dropping the first character from the input and appending the predicted character from our previous run, and generating another character from the model. We continue this 100 times and generate and print the resulting string. The string gives us an indication of the quality of the model. Then we train the model in batches and test output generated at each step by adding this for iteration block of code. After that, we will be testing the model. For that, add few lines of code. It allows us to randomly choose a row from input characters, then used it to generate test from model for the next 100 characters. In order to move forward with the test character plus the Y prediction value, we add this test character line of code. Finally, add a print statement. Save this file as alice_char_gen_rnn.py. Now we are set to run this code in our terminal. Go to our terminal and navigate to our Section 2 folder. Once we navigate to our folder, run our code using Python alice_char_gen_rnn.py file. You can now see the output of this run. As you can see, the model starts out predicting gibberish, but by the end of the 25th epoch, it has learned to spell reasonably well, although it has trouble expressing coherent thoughts. The amazing thing about this model is that it is character-based and has no knowledge of words, yet it learns to spell words that look like they might have come from the original text. Generating the next character or next word of text is not the only thing you can do with this sort of model. This kind of model has been successfully used to make stock predictions. Let's move on to RNN topologies. The APIs for MLP and CNN architectures are limited. Both architectures accept a fixed-size tensor as input and produce a fixed-size tensor as output, and they perform the transformation from input to output in a fixed number of steps given by the number of layers in the model. RNNs don't have this limitation. You can have sequences in the input, the output, or both. This means that RNNs can be arranged in many ways to solve specific problems. Next, we will look at back propagation through time. Just like traditional neural networks, training the RNN also involves back propagation. The difference in this case is that since the parameters are shared by all time steps, the gradient at each output depends not only on the current time step, but also on the previous ones. In this video, we learned about simple RNN cells and RNN topologies.